All right, 6.4. So 6.4 again is another very short section that I'm not a huge fan of, but I'm going to talk about it. This video should be pretty short. We'll just do one quick example of it. In 6.3, we did arc length stuff. In 6.4, we're going to be doing surface area. So we're going to be looking at those same solids of revolution we did with the washer and the shell method kind of things. But now instead of finding the volume of the interior, we're going to be finding the area of the surface of this solid we create. Now there's, again, a lot of really interesting stuff that's going on behind the scenes, a lot of difficult stuff. So I'm going to kind of gloss over that and just go through it real quickly. If this was the image that you were trying to find the surface area of, let's say you wanted to paint it or something, you want to know how much paint to get. What we're going to do is we're going to do what we always do, and we're going to partition the interval on the x-axis here from A to B into n different partitions. Then we're going to look at just an individual partition, so maybe we're looking at this one from xk minus 1 to x sub k, and we're going to end up with this tiny little length here on the outside of the surface. We're going to approximate that tiny little length using a straight line, and then we're going to revolve just that straight line around the x-axis. This creates a shape that's called a frustrum. I'd never heard of that before, but just think of it kind of like a megaphone shape, frustrum. And if you were to stretch that frustrum out, it would actually be a rectangle. So we're going to approximate these surface areas by looking at the tiny little rectangles that are created as you go along the surface. Okay, so again, a lot of math behind it. Some mean value theorem stuff shows up again, but the end result is just a nice little formula that helps us find the surface area, and it's this here. I say nice, I know it's kind of ugly looking, but I promise it's not too bad. So the area of the surface is the integral from A to B, 2 pi y, or you can think of that as a function of x instead, just f of x, square root of the same thing we had from arc length, 1 plus this derivative of the function squared dx. So it doesn't really matter which way you think of it. I think this is probably the easier way to think about it, the second one here. But let's just do a quick example. We'll do this one. Find the area of the surface generated by revolving the curve y equals 2 square root x from 1 to 2 about the x-axis. And here's the shape that we end up getting. All right, moving over to OneNote. So y equals 2 root x from 1 to 2. All right. So we also need the formula. So just copying the formula down, the surface area is going to be the integral from A to B. That'll be 1 to 2 for us of 2 pi, the function itself, f of x, times the square root of 1 plus the derivative of the function squared dx. All right, so just to double check, make sure I got that formula right, because I don't have it memorized. Yeah, looks good to me. Okay, cool. So we're just going to plug it in. We already have f of x, right? That's the 2 square root x, but we do need its derivative, so we can plug that into our formula here. The derivative of 2 square root x is that's an x to the 1/2. We're going to bring that 1/2 down, which will cancel out with the 2, and then subtract 1 away. This is actually going to be x to the negative 1/2. All right, plugging all that into the formula now. The surface area for us is going to be the integral from 1 to 2 pi, and we could pull that 2 pi out if we really wanted to. F of x, which is just the formula that we're given, 2 square root x, times the square root of 1 plus, I'll write it all out for now, this x to the negative 1/2 squared dx. X to the negative 1/2 is the same thing as 1 over the square root x, so you can think about it that way as well if you really want to. Okay. I'm going to pull the constants out. We have 2 times 2, which is 4. We have a pi that we can pull out. Other than that, it's still the integral from 1 to 2. We still have the square root x out in front, and we have the square root of 1 plus. So I'm going to go ahead and square that, thinking about it like we did up here. When you square that out, it's going to be 1 over x. Okay, this is a little trick that we're going to see quite a lot, and especially these, is that whenever you have 2 square roots together, you can just multiply the insides of those square roots together. So basically, we're just going to distribute this x inside of this square root. So when you multiply square roots together, you just multiply the insides. So we still have the 4 pi, we still have the integral from 1 to 2, but now combining these square roots and distributing the x times 1 is x times 1 over x is just 1. Alright, to do the antiderivative here, it would be another u substitution. We'll let u be the inside x plus 1, which means that my du would just be dx. Substituting all that in, we still have the 4 pi, still have the integral. This is now just going to be the square root of u, and then my dx changes to du. This would have antiderivative now, 4 pi out in front. We would raise this up to 3/2 and then divide, so 2/3 u to the 3/2. Substituting back in my u, which was x plus 1, remember, we're going to have the 4 pi, we're going to have the 2/3, and now it's x plus 1 all to the 3/2. That we're evaluating, remember, between 1 and 2. This is usually where I would ... this and just move on, but the video is short enough already, so go ahead and finish it off. So here, if I plug 2 into this, this is going to be 2 plus 1, which is 3 to the 3/2, and there's not really much we can do about that. Simplifying the stuff out in front, 4 times 2/3 is 8/3 pi. Plugging the 2 into this, we get 3 to the 3/2, so we'll just leave it like that for now. Minus, if I plug 1 into that, I still have the 8/3 pi. 1 plus 1 is 2, so then we're going to end up with 2 to the 3/2. I would honestly just leave it just like that, because there's not too much that you can do to simplify that down. So just leave it like that. I promise if you plug that into the homeworks, it'll count it right, as long as you did everything else right up top here. But that's good enough for me to have it simplified down. I'm guessing what the book probably does is they go ahead and factor out that 8/3 pi and write it like this. So 8/3 pi, and then just 3 to the 3/2 minus 2 to the 3/2. I'll go over to the book to see how they write it. Probably on the next page here. They write it like this. Yeah, so same thing, right? 8 pi over 3. 3 to the 3/2 is the same thing as 3 to the 1 times 3 to the 1/2, so they write that as 3 root 3. 2 to the 3/2 is the same thing as 2 root 2. Okay, cool. They also do a quick example here as well of integrating with respect to y instead of integrating with respect to x, but I hope it's easy enough to see. It's the same exact formula, you just have them as functions of y's instead of functions of x, so it's no different. All right, great. So that's it for section 4, which means that's it for your homework that is due this weekend.